Hi, afternoon everyone. We'll be starting class in about 1 to 2 minutes time. Alright, afternoon everyone. So today's lectures are basically going to be the second convolution lecture and the starting of what we'll be observing with respect to first and second order systems, in particular with respect to the transient response and the steady state response of these systems. Now, for this particular lecture, Convolution 2, in the last lecture that we did yesterday, we saw that for Convolution 1, we basically formulated the convolution integral from the convolution sum equation. And the convolution integral is actually what's going to be playing a very important role as to actually how do we evaluate convolutions in the time domain. And that forms the basis of what we're going to be doing in this lecture, Convolution 2 here today. So later on in this lecture in particular, we'll be doing some worked examples as to how we can actually apply convolution to two signals themselves in the time domain. And you'll see step by step as to how we actually resolve and obtain the resultant equations for each part of the convolution process as it is. So typically, when we have been actually doing convolution throughout the entire degree so far, we have been relying on the Laplace transform equivalent because we saw in the previous lecture that the convolution in the time domain is basically a multiplication in the Laplace domain. And it also holds true in the opposite way. A convolution in the Laplace domain will be a multiplication in the time domain as well. And typically, this works once we know that we can obtain a Laplace equivalent for x of t here being x of s, and h of t here being h of s. But not all the times you're going to get a Laplace equivalent for x and h accordingly. And sometimes it's necessary to manually evaluate the convolution integral in order to get your results in terms of the time domain. So that brings us back to our convolution integral equation here, where we have x of tau and h of t minus tau being integrated with respect to d tau here. And we're going to have to watch this with respect to how we will have two functions, x of t and h of t here, and how do we manipulate these signals accordingly to get into the x of tau and to ht minus tau before we actually start evaluating the convolution integral itself. So let's say we have two arbitrary continuous time signals here, x of t and h of t. Our first step would be to just change the variables from t to tau. So this here now becomes x of tau, and this here becomes h of tau, where our x-axis here would be respect to tau. The next step would be that, okay, we have our x of tau signal, but now we have to get this h of tau into h of t minus tau. So the first thing that we do for h of tau, we look at the x-intercepts here. Let's say the positive one here was tau 1 and the negative one here was minus tau 2. We then say, okay, if this is the h of tau signal, we reverse the entire signal accordingly to get h of minus tau. So tau 1 here will now become negative tau 1 here, and negative tau 2 here will now become positive tau 2 here because of this reverse of the signal. And then, in order for it to be t minus tau, well, let's say in this case we had t1 minus tau. This comes like we just, for every x-intercept that we have here, we just add the t1 variable accordingly. So this minus t1 here will now become, sorry, this minus tau 1 here will now become t1 minus tau 1 with this intercept. The center point, or basically the center of our original h of minus tau equation here, will now be t1 here, and then the next intercept here, which was tau 2, will now become t1 plus tau 2 here as well. And the reason for this t variable here, because this t variable can take any value, so this allows us to slide the h of t minus tau signal accordingly, depending on the value of t here. For it to be like, okay, we wanted to slide more to the left, or we wanted to slide more to the right, depending on the value of t here. But this signal here to slide accordingly. So in evaluating the convolution integral, now that we actually have x of tau and h of t minus tau here, this basically means that since we have our x of tau here signal being stationary and not moving, and we have flipped the h of t signal basically to be h of t minus tau accordingly. Sorry, we flipped the h of tau signal to h of t minus tau accordingly. This means now that the h of t minus tau signal here, because this can take any value of t, the signal here slides from left to right across the x of tau signal here. And for each slide instance, which you're going to see in the worked examples, there's going to be some overlap between the two signals. And when there's an overlap, this is where we'll be actually evaluating this integral part here, where the limits for the integral would be the uppermost limit where the overlap ends, and the lowermost limit where the overlap also ends as well. So the uppermost limit will be substituted here where we have positive infinity, and the lowermost limit will be substituted here for negative infinity. And then because we have the equations for x of tau and h of t minus tau, we can then evaluate the integral accordingly for each overlap section as of such. So typically we flip the h of tau signal and into h of t minus tau, and then for different values of t here, we slide it across the x of tau signal and we calculate the area of the product being the overlap zone for each slide. So let's watch this in a physical question example as to how we'll actually be applying convolution accordingly. So let's say we have a temperature control block diagram here, where we have a summing node, where we have a negative part here as well and a positive part, given a resultant positive equation. We have a constant gain block here, and then we have an integrator block here accordingly throughout the entire system. We also have the output here feeding back into the input in a negative form represented by this minus sign here. So if we want to resolve the output equation here of the entire system, we first watch at the summation junction here, and we say, okay, this is x of t, and we have y of t feeding back here, and it's negative, so that's x of t minus y of t, and the output of the summation junction here results in a of t. So that means we have already taken care of this x of t signal here and this y of t feedback signal here. So we just only need to focus on this forward part here only. So at this point, we can say basically y of t is going to be k a of t, and then that entire thing needs to be integrated in between t and negative infinity. And this will be with respect to dt since it's an integral equation. So y of t here, because we also know what at is here, meaning x of t minus y of t, we can substitute this into the equation and get the final form here in terms of its inputs x of t and its outputs y of t. For our integral, however, because we're doing it with respect to dt, we have limits of t to negative infinity, we just switch the variable here to tau, so that we can substitute t and negative infinity here accordingly for this mathematical equation. So now that we actually have y of t in the integral form here, maximizing our inputs x and our outputs y here, the questions will basically ask for us to find the impulse response and then a temperature change produced by the system when the gain k has a certain value here, being 0.5, and we have an input step change of 0.75 degrees with a respective time here being at t equals 4 minutes. So the first part of the question basically asks us to find the impulse response. So because this is an integral equation, we can differentiate the entire equation here. And because it's a differential form, we can basically apply the Laplace transform here to solve it accordingly, or we could do the long way and do the solving of differential equations using the time domain. And you'll end up getting this equation here being h of t equals to k e to the negative kt u of t. The second part of the equation basically says, okay, the second part of the question, sorry, basically give us values for k, the step change being the inputs, and the value for t here. D tau and dt basically are the same thing for this question because how the limits here for the integral are t and negative infinity. We can't say x of t, y of t here to substitute in t here accordingly. Mathematically, that doesn't make sense. So we just basically use a substitute variable here known as tau to conduct the integral as of such. But yes, basically from a concept standpoint, d tau and dt basically are the same thing, where d tau, after you conduct the integral, you just substitute in t here to evaluate the entire equation and get the result back in terms of t only. So for the second part of the question, we basically have our gain here equals to k equals 0.5. We have the step change of 0.75 degrees representing our x of t signal, and the time at which it occurs being that t equals to 4 minutes. And basically, because we know what x of t is here, being there's a step change of 0.75 occurring at t equals to 4, we can have a resultant equation here for x of t being equal to 0.75 u of t minus 4, because this is just basically a shifted shifted step equation where we start at t equals 4 with a magnitude of 0.75. And from the impulse equation we saw on the last slide, we basically solved for h of t here. And we got it basically being that since it's a linear time invariant system, h of t here will start at t more than equal to 0, and for anything less than 0, it's just basically going to be 0. And the resulting equation, when we substitute in k and our other values here accordingly, will be 0.5 e to the negative 0.5 t as well. So now that we actually have an x of t signal here and an h of t signal, we actually can perform our convolution here accordingly to get our resultant y of t signal. So, as we saw from the convolution integral equation, we require our signals to be as x of tau and h of t minus tau. So, x of t transformed to x of tau is we just replace the variables from t to tau accordingly. So, it'll become x of tau equals to 0.75 u of tau minus 4. And for h of t minus tau, that basically means we had to flip the entire signal after we made it h of tau to h of minus tau, and then we'll add our t variable here accordingly as of such. So, because we flipped the signal, and it was in this form here for h of t, When we say h of tau, it's basically the same thing here. But when we say h of minus tau, it comes like this part of the signal is on the left-hand side, and this part here is going to be on the right-hand side. Yes, it's supposed to be t more than equals 0. I'm fixing that now. Thank you for reminding me about that. Right, so just recapping a little bit. We need h of t minus tau. So we say h of tau first. So this just changed t to tau here. And then we flip the signal to get h of minus tau. And then we say, okay, it's going to be t minus tau. So that comes like we just add the t variable. So this x-intercept here now becomes t accordingly, as we can see here, for a resultant h of t minus tau equation. And the equation itself here, for where we had the mathematical representation, everywhere that we had t, it's now replaced by t minus tau accordingly in the equation. And for limits, where we had t more than equal to 0 and t less than 0, we would have t minus tau more than equal to 0 here. Fix that as well. And we're going to have t minus tau here being less than 0 for the second half of our equation for h of t minus tau. So in doing our evaluation here for our convolution, we consider doing this in a series of cases or steps accordingly. So we first, because we know the x of tau signal here is remaining stationary, and then we have to say the h of t minus tau signal is what we're sliding across it. We consider the first instance where we had for t being less than 4. So this t-intercept here on the h of t minus tau signal is going to be less than 4 here, where our actual x of tau signal starts. And basically, we can see that if we watch where the signal overlaps, it's basically for this entire thing here, it's just going to be 0 multiplied by the entire signal. So the entire resultant of y of t here, for t being less than 4, will result in an overall value of 0 accordingly, because we just basically multiply by 0 here. So this is going to be our first case when we start sliding for our convolution. Our second case would be after we pass 4 on the x of tau scale here, and now our h of t minus tau is where t is going to be greater than or equal to 4. So in this case, this means that the overlap range will be this part here accordingly, because here it's just basically going to be 0, and here's also 0 accordingly. So we're only focusing on the range here that will give us a positive value for the overlap. So for this case, when we apply it into our convolution equation, the limits of the integral, because the integral overlap only exists in between this section here, it's in between t and 4. So our uppermost limit for the integral will be t, and our lowermost limit here would be for 4. And x of tau here, we know, was basically 0.75 u of t minus 4, but because we know it's u of t minus 4, we just say 0.75 here for integral equation. And our h of t minus tau signal for this curve here was 0.5 e to the negative 0.5 t minus tau, and all this is being integrated with respect to d tau here, and then we'll substitute in our uppermost and lowermost limits to get it back with respect to t to obtain y of t here. So in evaluating this integral, what we'll end up after we do the integral evaluation here, and we have automatic integral calculators online that which you can use to actually evaluate this integral for you, you'll end up getting a resultant equation here of y of t equals to 0.75 1 minus e to the negative 0.5 t minus 4. Well, the u of t minus 4 basically means that's where the unit step actually starts accordingly. Basically, if we plot this entire y of t equation here, and we see the response, we see basically until it reaches a value of 0.75, it will take about 6 minutes accordingly to hit the set temperature, which was asked accordingly in the question. So this red line here represents our y of t signal, and the blue line here represents our x of t signal. The y of t signal here being our output, and the x of t signal here being our input. And we're watching the time for which the y of t signal approaches the x of t signal accordingly, because our x of t is basically being our set point that the y of t signal needs to reach. So, in plotting it, you basically see that it's going to take about 6 minutes for the input from the input to reach the close to the set temperature for the output. Alright, so are there any particular questions regarding this convolution theory so far? And I know it might seem a little bit confusing, but when we actually start doing the worked examples later on in this lecture, it will become a little more clear as to how we're doing the actual convolution process itself. So this value of 10 here is observed by plotting the y of t signal accordingly. Because we know the y of t signal here, when we plot it, it's going to be 0 for everything less than t being 4, and then the y of t signal here basically turns on accordingly. So basically how we realize that it takes 6 minutes is that we watch where the y of t signal actually hits this value of 0.75. So, and then we solve for t accordingly to figure out, okay, what's going to be the time at which it occurs. And then, because we know this time at which it occurs, and then the start time here, that's how we end up getting 6 minutes, being the difference between the two times. Another way to solve it without plotting the equation of y of t is just say y of t here is equal to 0.75 on the left hand side, and then solve the equation accordingly to get the t value as well. Tau is just basically a placeholder for t. That's all it is. Because remember, when you conduct the integration here, basically you need a substitute variable to basically have the equation resulting in tau, and then wherever tau is, you substitute in t accordingly as your limits for evaluating the integral. So that, as of such, when you get the end result, it will be with respect to t here accordingly, instead of being with respect to tau because of the substitution for the integral limits. So tau basically is just a placeholder to conduct the integral, and then you substitute in your t variables accordingly to get the entire final result with respect to t. That's all it is. It's just a placeholder. And it'll become a little more evident as we start with the worked examples as to why we're using tau as a placeholder when we conduct our integral evaluation. Right, any further questions at this point? Yes, the u of t minus 4 was added because we know where the signal actually starts accordingly. And that's because the signal starts at t equals 4. Yep, basically after the integration. That's the only reason why we put it there, because we know the actual time at which the signal starts, and that's going to be at t equals 4. But the u of t minus 4 with respect to the shift, yeah, it's basically the same thing with respect to the shift. It can be any point before the start of it. Yes. So when you're doing the shift, basically, but the cases when we observed it, go back one, we basically had two time instances because we're watching for where t is less than 4, and this is before this signal has any overlap. The h of t minus tau signal has any overlap with the x of tau signal. And then the second case would be where the h of t minus tau signal actually overlaps accordingly with the x of tau signal here. And we know that we have a time instance for where it's going to be t more than or equal to 4 in this particular case. And yeah, this will become a lot more evident when I start doing the worked examples later on in this lecture as to why do we consider values for t here accordingly while we're conducting our integral. And this actually is quite important for substituting the limits for the integral as well when you have your overlap zones. So in this case, yes, it can be for any point before the start and ending of x of t. But you're going to see in the worked examples why do we choose particular time points to help us conduct the integral evaluation. And I'll elaborate on that a little bit further on in coming down to the worked examples in the lecture. Alright, so before I get to the worked examples, I just need to briefly discuss some properties of the convolution integral. The first property that we're dealing with here is that the convolution can be performed in any order which you wish. So you can hold the x of t signal here constant and then slide the h of t signal accordingly, or you can hold the h of t signal constantly and slide the x of t signal. Both will result in the same answer. It doesn't matter which order you do the convolution, it's basically going to result in the same final answer. If you convolve any arbitrary continuous signal here with a unit impulse, this basically results in just getting back the original signal accordingly because of the shifting property of the unit impulse that we saw in previous lectures. With associativity, where if let's say we had some bracketed forms here for a convolution and then you had another convolution, saying that you had to do two convolutions here, the first one being x of t and h1 of t, and then the result being h2 of t. It still doesn't matter which order you do the convolutions in. You can perform h1 and h2 first and then convolve the result with x. It doesn't matter the order in which you do it. You will still end up with the final answer accordingly. And this convolutions in sequential order here basically results in what we refer to as a cascaded system. because it comes like we do x of t here, then convolute with h1 of t, get our result, and then we convolute with h2 of t as of such. So it's basically just a cascade system for the associativity property. If you have the convolution of something, but in the brackets you have the addition of two signals, this is similar to like if you convoluted x of t and h1, and then you add the results to the convolution of x of t and h2 accordingly as of what. And this is the distributivity property, which results in a parallel system, as you can see here. So the convolution properties for associativity and distributivity is basically like similar to the properties of multiplication. And once you just remember that it's similar to the properties of multiplication, it basically is going to be the same thing, just it applies to convolution instead. Alright, so we're going to start with our in-class problems that I'm actually going to do on the whiteboard here for you guys to see how actually do we solve these accordingly and how do we get our resultant convolution equations as of such. So at this point in time, please make sure that you memorize the signals here for x of t and h of t, and I'm actually going to do this on the whiteboard for you guys for how you evaluate the convolution. And yes, it looks a little bit difficult, but the reason why we're doing the work problems here is to show you that it's not difficult at all. It's just a little bit tedious and repetitive as to how you actually conduct your convolutions. Bring this down. I'm keeping my ink annotations here for the corrections. Alright, so that's what we're going to be using. X of t and h of t. Alright. So we have an x of t signal here. Being this here being 0, 2, magnitude of 1. And our h of t signal basically means the same thing. And we're going to have to get these in terms of x of tau and h of t minus tau. So for this to be x of tau, it's basically going to be the same signal. Our axis here now becomes tau. Our h of tau signal is basically the same thing as well. But remember, we need to get h of t minus tau. So because we have h of tau there, we then obtain our h of minus tau signal. Comes like if we flip the entire signal accordingly. So this now becomes 1, 0. This here becomes negative 2. So this will be h of minus tau. And then, because we need to add that t variable here, this now means that that t variable can take any value. So this being h being ht minus tau means that for everywhere we had a value on the x-intercept here in particular, this now adds t accordingly to these values. So where we had 0, this here would now become t, and where we had minus 2, this now becomes t minus 2 for x-intercepts. So this here becomes t, this way becomes t minus 2. So now that we actually have our x of tau signals here and our h of t minus tau signals, we actually can start doing the convolution process that we observed. So we can say here, for case 1, let's actually start doing our overlap process here for x of tau and h of t minus tau. So we draw our axes here, and we put our x of tau signal here accordingly. We're going to use a different color ink here for the h of t minus tau. Okay, so before I continue, let me see these questions here in particular. Alright, so the first question we have here is where exactly is the y-axis for the h of t minus tau graph? So because we substitute in t here, and t can take any value, there isn't going to be a y-axis here, because this now means that the h of t minus tau signal can slide accordingly. So it can, because we can say here, okay, that t equals 0, so it's going to be t0 and minus 2. But then we can say t is equal to 1, so this will be 1, and then this will be positive 1 here accordingly as of such. So that's why we don't draw a y-axis here for h of t minus tau, because this signal here is going to slide and change accordingly to respect to the values of t as we keep on evaluation. Y of t is going to be our result in the graph. So we haven't actually obtained this as yet. This will be obtained when we start evaluating the convolution integrals for each one of these cases. So in evaluating case 1 here, we can see that t here for h of t minus tau has not even hit the value of 0 here. So we basically say this is going to be t less than 0. And because there's no overlap, this means y of t here is going to be 0. So that will be our first case, where there's no overlap of the two signals. So let's go on to case 2. And for case 2, we're also going to draw back our axes here again. And we're going to draw our x of tau signal. But we're not going to slide our h of t minus tau signal here accordingly for case 2. So that way, that t-intercept that we saw here in particular is not going to be more than 0 accordingly. But we're going to see here that this point here in our graph for x of tau was basically if we were at 1. So we're going to make sure that this leading edge here for h of t minus tau is going to be in between 0 and 1 here accordingly for case 2. So in evaluating the time range for this, we know t is more than 0, but it can also be more than and equal to 0 depending on how we say it. So we say t here is more than equal to 0, and t here hasn't reached the value of 1, so it's going to be t less than 1. And if we combine these two inequalities here, we basically get 0 less than equal to t less than 1 being our effective time range. We know that the convolution integral is represented by our y of t equation here. And that our overlap for these signals exists only for this part here that's shaded in green. So I have another question here where when you say t less than 0, do you mean with respect to the signal shift, as in h of t minus tau is the same as h of tau minus 1? Yes, it's basically, it's with respect to the signal shift. So that's why we evaluate those time ranges to say, okay, this is the time range for which h of t minus tau exists for this particular shift. So because we have an overlap of our x of tau signal here and our h of t minus tau signal, this comes like y of t here, when we evaluate our integral, is going to be in between t here and 0, where t is being the uppermost limit of our overlap, and 0 being our lowermost limit of our overlap. There's going to be t here and 0 here. X of tau has a constant value of 1. H of t minus tau also has a constant value of 1. This is being integrated with respect to d tau. So if you do this with respect to d tau, this is like if we integrate on 1 d tau, so we get a resultant value here of tau, and we substitute in our integral limits here being t and 0. So this comes t minus 0, which gives us a result of t. So this might also answer the question we had earlier as to why do we use tau. And mathematically, we just use tau as a placeholder for when we substitute in t to get back the y of t equation being in terms of t only. So that's going to be our second case here. Our third case is where we're going to slide the h of t minus tau signal again, but now that t-intercept that we saw here, instead of it being in between 0 and 1, it's now going to be in between 1 and 2. So this will be case 3. Case. So we have our x of tau signal here. But let's frame this one part here. And we now slide our h of t minus tau signal towards for the t-intercept for it to be in between 1 and 2 of the x of tau signal. So for case 2, the reason why we use t and 0 as limits as opposed to 0 and 1 is because we're only watching where the signals overlap with each other here. So when we watch where the signals only overlap with each other, in this particular case, we see here that the uppermost limit is just going to be t, and the lowermost limit here is going to be 0. So that's why we use those limits, only for where the signal overlaps with each other. Because this leading edge here for h of t minus tau has not even approached a value of 1 here accordingly. So the overlap is just only occurs for where the integral exists, so that's why we say it's in between t and 0 accordingly. So for case 3 here, we have our x of tau signal which remains constant, but we're going to slide our h of t minus tau signal again, such that our leading edge here, the t, is now in between 1 and 2. And this part here is still here for being t minus 2. The point of the whole inequality is going to come towards the final answer, because you're going to see that the output convolution is a piecewise continuous function. We're considering 1 because we're watching this in terms of how we actually do the slides accordingly. And in particular, when I start evaluating case 3 here, you saw that the time range here was in between 0 and 1. The time range for case 3, when we evaluate it, is going to be in between the time range. Instead of it being 0 and 1, it's now going to be 2 and 1 accordingly. And you're going to see why these time ranges play an important part in evaluating the convolution integral. So, in watching where your signal overlaps with each other, it's going to be this shaded area here. Well, now let's evaluate the time range for this shift with respect to h of t minus tau. So we see t here, and we know t has crossed this 1 mark. So we basically say t here must be more than or equal to 1. But t here hasn't crossed the 2 mark for x of tau. So you say t is less than 2. If we combine the two inequalities here, we get 1 less than equal to t less than 2. So yes, it is automatic. We assume the first shift to be less than 1 and then the second shift to be greater than 1 and less than 2. And the reason for why we do this is evaluating the time ranges here accordingly. So you can see here that for case 2, our time range here was 0 less than equal to t less than 1. But for case 3 here, our time range here is 1 less than equal to t less than 2. And similarly, when we watched it for our first case, t was less than 0. And like I say, these time ranges play an important part for when we evaluate the convolution integral. So we see here, basically for each convolution case that we observe here, the time range is always going to be a width of 1 unit when we evaluate the convolution. And that's why we do the slides here in this particular order, to make sure that the evaluation range is always going to be a time width of 1 unit. So yes, the equation for case 2 is going to be valid for t from 0 to 2 rather than just 1. But the reason why I'm doing this in steps of 1 time unit width is to show you guys that it's always important to observe this 1 time unit width. So you'll see why it is this way when we start evaluating the convolution. Why it is always important that you evaluate with respect to 1 time unit width. So for this particular case, we know that our time range here is going to be 1 less than equal to t less than 2. And if we evaluate our convolution integral, so we know it's y of t in positive infinity and negative infinity of x of tau ht minus tau d tau. Our integral range here for overlap is now going to be t and 0. Because t is being our uppermost limit for overlap and 0 being our lowest limit here for overlap. X of tau was just 1. And h of t minus tau also a value of 1. And that results in this being tau when we evaluate the integral between t and 0. It also results in a value of t. Now, for this particular case, for this particular convolution, we see here that case 2 and case 3 ends up with the same end result. Because we see here for case 2, we end up with a value of t for y of t. And for case 3, we also end up with a value of t for y of t. But the reason why I'm doing this with respect to 1 time unit width is that this will not be the event that will happen throughout all your convolutions. there will be events where that for each time unit width of 1, depending on your time range, you're going to end up with a different result for y of t accordingly. So it's always important to evaluate this with respect to 1 time unit width. When I evaluate case 4 here, you'll see why this is important, because for case 4, the y of t equation is going to change for the next time range. So for case 4, we're going to draw back our axes here again. We're going to draw our x of tau signal. And we're going to slide that h of tau signal accordingly again, such that the leading edge here, being t, is now outside our signal, but our fallen edge is still inside our signal here accordingly. So for this particular convolution, there will be no changes in the equation x and h, because they're always going to be a value of 1. But when you start doing convolution with piecewise continuous signals, you want to see that the equation will keep on changing accordingly for where you have your overlaps. So because we slide our h of t minus tau signal here again by 1 time unit, our overlap exists for this part here. And the reason why the overlap exists for this part is because when you watch the value of 1 here in between t and 2, this is going to be a value of 1 here being multiplied by a value of 0. So we just get an end result of 0. So we only consider this part here where the signal overlaps accordingly. So in evaluating the time ranges here, we know that t has crossed the value of 2 here. So we say t is more than or equal to 2. But t here hasn't reached a value of 3. So we say t is less than 3. And if we combine the two time ranges, it's going to be t less than or equal to t less than 3. Now, when we start evaluating the convolution integral here for case 4, we're going to see that we're going to end up with a different equation entirely for y of t. So, y of t, in evaluating the convolution integral, as we keep on seeing, was x of tau, h of t minus tau, d tau. We substituted our limits, and then for overlap, the uppermost limit here was 2. But the lowermost limit here is going to be t minus 2. X of tau was 1. H of t minus tau was 1. D tau. So we get tau here. But we now have different limits when we start evaluating this. So this comes like, when we substitute this limit here while we're evaluating our integral, we get 2 minus t minus 2. And that would give us an end result being 2 minus t, and this minus sign here will be multiplying by this negative 2 here, will give us positive 2, so we get 2 plus 2, so that's 4 minus t. So we see that here for case 4, we end up with a different y of t equation when compared case 3, we had y of t being a result of t. And for case 2, we also had y of t resulting in t. Now, we have one more case to evaluate, and this is when the h of t minus tau signal has finally finished sliding across the x of tau signal. So this is going to be case 5. Draw back our axes here accordingly. And in this case, because we see that the h of t minus tau signal here is all the way on the right hand side, meaning that it's finished sliding over the x of tau signal, basically there's no overlap, so y of t here is going to be 0, but we still need to evaluate what our time range is going to be. So a nice way to evaluate the time range for this part here is that we know that this intercept here, t minus 2, is going to be more than 2. So we say t minus 2 is more than 2. So in this case, t is just going to be more than 4. And we have no overlap. So y of t is equal to 0. So when we combine all the results here for each one of these cases, we're going to see that y of t from the convolution evaluation results in a piecewise continuous function. So we have y of t here, and we know that it's going to be 0 for t less than 0. I'm going to backtrack here for you guys to see that from case 1. For case 1 here, t was less than 0 here, so y of t was 0. For case 2, for the time range 0 less than t less than 1, y of t was equal to t. And this was the same thing for case 3, where y of t is equal to t for 1 less than t less than 2. So I'm going to write that in at the end here. So this was t here, for 0 less than equal to t less than 1. Also t here for 1 less than equal to t less than 2. And because we have the same y of t here for these time ranges, we can just combine the time ranges here accordingly. So we can erase this, and because we know that the uppermost limit here is t less than 2, we say 0 less than t less than 2, because it's basically the same equation. And we saw for the next time range here, 2 less than equal to t less than 3 for case 4, we had a resultant equation here being 4 minus t. 4 minus t, 2 less than equal to t less than 3. And then for our last part, which was t, oh sorry, something wrong here. Yes, I actually missed out a case. Yes, I did miss out a case. Oops, my bad. So I'm going to come back to that, because we are missing a case. We missed out the entire case. Alright, so I want to leave a blank spot there for the case that we actually missed, because we need to evaluate for 2 less than equal to t less than 3, but we didn't actually get the resultant equation for this. So we had 4 minus t with 3 less than equal to t less than 4. And that's because no, whoops, right here. Sorry, my mistake. I understand what I'm doing wrong now. So four minus t here. Right. Well, we didn't evaluate this for 3 less than equal to t less than 4. Right, that's true. And then we had 0 here being t more than 4. Right. So we had one more evaluation to conduct, as you rightfully pointed out in the chat, which would be for this time range 3 less than t less than 4. So let's run this evaluation here underneath. So this would have lied in between cases 4 and 5. So let's just call this case 4.5. No, it will not be less than or equal to 4. It will be t less than 4. For this particular case, we can say t more than or equal to 4. We can say that for this particular case if you want to include the more than equal sign. Right. So for case 4.5, where we're going to get our output time equation range here being 3 less than or equal to t less than 4, we're going to draw back our axes here accordingly. This will be for x of tau signal. And we're going to draw our h of t minus tau signal here. It'll be t here, and this will be t minus 2. Will be 1. I'm just going to backtrack a little bit to make sure I drew this correctly in the previous one. Yes, I did draw it correctly in the previous one. Nice. And this here would be 3. This here would be 4. No, in this particular case, the signals don't overlap. Even that you're saying, okay, there's an input at 4. But because the signals doesn't overlap, you just get a resultant value of 0 when you conduct the integral. Right. Right. So our overlap here for case 4.5 will be this green shaded area here. And in evaluating our time range, we see that t here in particular is across the 3 mark here, but it's still less than 4. So we say t here is more than equal to 3, but t is less than 4. And then we combine the time ranges, so we get 3 less than equal to t less than 4. And then when we evaluate our convolution integral, so h of t minus tau tau, we substitute our limits here being 2 and t minus 2 for our overlap zone. X of tau is 1, h of tau is 1, so we get tau here being in between 2 and t minus 2. at 2 minus t minus 2 gives us a result of 4 minus tau here, minus t, sorry, accordingly. So we get 4 minus t here as well for that time range of 3 less than equal to t less than 4. And because we have the same equation here accordingly, we just combine these two time ranges here. It was less than 4. Just switch this here. 2 less than t, less than equal to t, less than 4. And that basically gives us our output equation for y of t being the result of a convolution. And if we plot this accordingly, so we're watching our y of t equation here, we can see that this being a piecewise continuous function, so we're going to say y of t is going to have an equation of t in between 0 and 2, and then 4 minus t, so 2 less than equal to t less than 4. When we plot y of t here being our output of the convolution of x of t and h of t, what this looks like here is a resultant triangle equation where this part of the equation here is t, but this part of the equation here is 4 minus t. So that's why it's important for us to conduct the integral evaluation for each case of the convolution using one time unit width. Because you saw here that when I skipped a step, I forgot to evaluate for 3 less than equal to t less than 4. And for this convolution, yes, we got the same equation for when it was 2 less than equal to t less than 3. But for other convolutions, that's not going to be the case. You may end up getting a different entire equation for y of t when you conduct this integral evaluation. So that's why it's very important to always conduct the integral evaluations for each case of the convolution using a time width of 1 unit. So always evaluate your cases with a time width of 1 unit. And to make sure that when you're actually evaluating this, you actually check when you're sketching the graphs here, when you're evaluating the inequalities, that you obtain the inequalities representing this time range of 1 unit. Alright, so are there any questions regarding this first worked example convolution in particular? If there's anything that I need to clear up at this point in time. Alright, so it looks like we don't have any questions regarding this particular convolution. So this was the first in-class problem that we did. We're going to watch for our second in-class problem here, where we had the h of t signal here shifted to the left by 1 time unit. Oh, okay, so we have a question here asking, how do you know how many cases to evaluate? Typically, because we know that the time ranges here for each one of these signals were basically 0 to 2, that means that in the end, when we watch our evaluation cases, so we went up to case 5 here, and we had an extra case here, 4.5, so that's going to be 6 cases in total. So typically, when we have a convolution like this in particular, because we know basically the same time ranges here, 2 and 2, that means we'll have 4 overlap sections for these time ranges, because this here is a time width of 2, and this here is going to have a time width of 2, and there's going to be 2 non-overlap sections, being when this signal h of t, when it's t minus tau, it's going to be on the left-hand side here, not intersecting with x of t, and it's going to be on the right-hand side here, not intersecting with x of t. So we'll have 4 overlap zones and 2 non-overlap zones accordingly, so you'll end up having 6 cases. And the reason for that is because we watch this with respect to the time width here for each one of these signals. So x of t had from 0 to 2, so that's a time width of 2, and h of t had a time width here of 0 to 2, so that's 0 to 2 as well. So that means when you add the 2 together, you get a full total of 4. So you will have 4 overlap zones, and then you have the 2 non-overlap zones when this h of t minus tau is going to be on the left-hand side here, and then when h of t minus tau is going to be on the right-hand side here. So you get this grand total of 6 cases. Right, so let's watch our second in-class problem here, where we still have the same x of t signal being 0 to 2. But now we have the h of t signal here shifted left by 1, and we're going to observe this where we're going to have to transform this accordingly to conduct the integral convolution evaluation as of such, using this new h of t signal as well. So remember, in this particular case, h of t, instead of it being, in our first case, 0 to 2, it's now going to be in between -1 and +1. And we're going to be conducting the convolution accordingly for this particular problem. Right, so let's play our whiteboard here. And we're going to draw our signals here accordingly. So we had our x of t signal here. And then we had our h of t signal here. So our first step would be to convert these into tau. So the x of tau and then we have h of tau we then need to flip the h of tau into h of minus tau. So it comes like if we just flip the entire signal, but because it's symmetrical about the 0 point on the x-axis, we just end up with the same signal accordingly. And then when we say we put this as h of t minus tau, because it comes like we just add t. Where we had our x-intercepts on the x-axis, it comes like we just add t accordingly to these intercepts. So where we had 1 here in particular, this now becomes t plus 1, and where we had -1 here, this becomes t minus 1. So now that we actually have our x of tau signal, and our h of t minus tau signal, we can actually start conducting our convolution evaluations for each one of these cases. So let's start with case 1. And we'll draw axes here accordingly. So our x of tau signal here. And then we have our h of t minus tau signal here. So we know there's no overlap. So y of t here is going to be 0, but we still need to evaluate our time range as of such. So for this particular case, we see that t plus 1 here hasn't hit the 0 part here for x of tau. So we say t plus 1 is less than 0, so t here is going to be less than minus 1. So that will be the evaluation for our first case here. So let's slide the h of t minus tau signal such that it's going to be where this t plus 1 line intercept here is going to be in between 0 and 1 for x of tau signal. So this is going to be case 2. So we draw axes again. Draw x of tau signal. And now we draw our h of t minus tau signal here. And we can see that where the two signals overlap, it will be in this green shaded region here. So, because we saw here that t minus 1 was less than 0, but this case, case 2, sorry I said that wrong. Because we saw here for case 1, t plus 1 here was less than 0. For case 2 here, t plus 1 has crossed the 0 mark. So this is going to be t plus 1 is more than equal to 0. So we get t being more than equal to negative 1. And we also know that t plus 1 here hasn't reached this 1 mark, so it's less than 1. So t here should be less than 0. If we combine these two inequalities here, we get negative 1 less than equal to t less than 0. So we have a question here asking which one is t for t less than equal to negative 1 and the ht minus tau has t negative 1 and t plus 1. Oh, okay, I think I answered your question. Yeah, okay, nice. Right, so in evaluating this, we basically saw here that t plus 1 here, it went more than the 0 mark here. So we said t plus 1 being this intercept is more than equal to 0. When we evaluate this, we get t more than equal to 1. And then t plus 1, the intercept here, is less than 1 because it hasn't actually hit this value of 1. So we say t plus 1 is less than 1. And when we evaluate this, we get t less than 0. When we combine the result of these two here, we get negative 1 less than equal to t less than 0 accordingly. Then, in evaluating our convolution integral, the limits for integration here will be t plus 1, where we have the uppermost limit for our overlap, and then our lowermost limit for overlap here is going to be 0. And the equation for x of tau was 1. The equation for h of t minus tau was 1. So we get tau here being evaluated for t plus 1, 0. So we end up getting a result here of t plus 1, case 2. For case 3, we're going to slide that h of t minus tau signal again. Such that the t plus 1 intercept now is going to be in between 1 and 2 here on our tau axis. So we draw our axes again. And put that intercept point here. But now we're going to put our intercept overlap, sorry. So t plus 1 being here. And then we have t minus 1 here. And our overlap zone is now given by this green shaded area here. So, in evaluating this time range, t plus 1 has crossed the value of 1 here. So we say t plus 1 is more than equal to 1. So as of such, t is more than equal to 0. But t plus 1 here hasn't reached our 2 value here. So we say t plus 1 is less than 2. So t here is less than 1. And then when we combine the inequalities, we get 0 less than t less than, sorry. Yeah. 0 less than equal to t less than 1. We then conduct our integral evaluation for a convolution. And we can see here for our integral evaluation, the uppermost limit of our overlap is t plus 1. The lowermost limit of our overlap is 0. So we substitute these as the integral limits. X of tau was 1. H of t minus tau was 1. So we end up getting tau here, being in between t plus 1 and 0. So we get t plus 1 accordingly. Right. So for the next case, we're going to slide this h of t minus tau signal such that the t plus 1 intercept is now going to be in between 2 and 3 here on the x-axis. Sorry, on the tau axis here accordingly. So let's evaluate case 4 here to see what this looks like. Right, nice. So we draw back our axes again. Draw x of tau signal. And now we put our h of t minus tau signal here. Represented our new shift accordingly. We watch where the signals overlap, and our overlap area with this part here shaded in green. And then we evaluate our time range. So for this case, we know that t plus 1 here has crossed the value of 2. So we say t plus 1 is greater than or equal to 2. And when we evaluate this, we get t greater than or equal to 1. T plus 1 here hasn't crossed the value of 3. So t plus 1 here needs to be less than 3. So t here is less than 2. And if we combine the two inequalities here for t, we get 1 less than or equal to t less than 2. In evaluating our convolution integral for this case, we see that the uppermost limit for our overlap is 2, and our lowermost limit here for our overlap is t minus 1. So we substitute these as our integral evaluation limits. X of tau was 1, h of t minus tau was also 1. So the integral evaluation will be tau with respect to 2 and t minus 1. So we get 2 minus t minus 1 gives us a result of 1 minus t. Sorry, 3 minus t. Now, one thing to notice in particular is that this t minus 1 intercept here, all the time that we've been watching it, the t minus 1 intercept here was before 0. And now in this case, the t minus 1 intercept here was in between 0 and 1. And if you don't wish to conduct the time range with respect to this leading edge, you can actually use the falling edge here as well to conduct the time ranges. But for our illustration purposes, we're using the leading edge because it's always simpler to use this leading edge to get this resultant time range. So let's evaluate case 5, where this t plus 1 intercept is going to be in between 3 and 4 on the tau axis, and the t minus 1 intercept here is going to be in between 1 and 2 here on the tau axis. So we draw our axes again. This being our x of tau signal. This will be 3, this will be 4. We know our fallen edge here, so h of t minus tau signal, t minus 1. This here is going to be t plus 1. And the overlap region for where the two signals have some overlap is going to be represented by this green shaded area here. So let's use the leading edge here to conduct our time range. But I'll also show you an example where we can use the falling edge here to conduct our time range as well. So t plus 1 here has crossed the value of 3. So we say t plus 1 is more than equal to 3. So t here needs to be more than equal to 2. But t plus 1 here hasn't reached the value of 4. So we say t plus 1 here is less than 4. So we get t less than equal to 3. And we combine the two time ranges, you see that we get 2 less than equal to t less than 3. A little bit jumbled, so let's write that a little bit neater. Right. We can say similarly, we can say we're watching our fallen edge here. So t minus 1 has crossed this 1 point here. So we can say t minus 1 more than equal to 1. So we get t more than equal to 2. And t minus 1 here hasn't hit a value of 2 here. So we can say t minus 1 is less than 2. Get t less than 3. And you can see here when we combine these two inequalities, we get back the same time range accordingly. In 2 less than equal to t less than 3. So in conducting our convolution integral for case 5, y of t is equal to integral range positive infinity, negative infinity. So h of t minus tau. Our integral limits here for overlap would be, the uppermost limit will be 2, and our lowest limit will be t minus 1. So we substitute those in. X of tau was 1, h of t minus tau was 1, We get tau here being evaluated in between 2, t minus 1. So we get 2 minus t minus 1. And we get a result of 3 minus t, which is similar to the result that we got here for case 4. And finally, our last case would be when the h of t minus tau signal has completed all its overlap of x of tau. So this will be case 6. And in this case, we know that t minus 1 has crossed the value of 2 here on our tau axis. So we say t minus 1 more than equal to 2. That means to be t more than equal to 3. And that corresponds with the evaluation of our time range here, where we had 2 less than equal to t less than 3. And there's no overlap for case 6. So y of t here is equal to 0. So when we actually draft our final answer here accordingly, for y of t, we know that it was 0 for our first case, and we're backtracking here to get to the cases. T less than -1. I'll backtrack again at this point in time. This is for t less than -1. And we saw it was t plus 1 for -1 less than t less than 0. T plus 1 again for 0 less than t less than 1. Verifying that by backtracking. This will be case 1 and 2. So case 2 and 3, sorry. So -1 less than t less than 0, t plus 1. And then 0 less than t less than 1, t plus 1 as well, right? Case 4 and 5, we had the same equations, which was 3 minus t for our next time ranges. So this will be 3 minus t, 1 less than equal to t less than 2, 3 minus t, 2 less than equal to t less than 3, and then 0 here, to t more than equal to 3. And we saw basically once we had these same equations, we could just combine the time ranges accordingly as of such. So yes, the convolution stuff is tedious, but it's simple and it's just repetitive. You just have to pay attention when you're sliding the h of t minus tau signal. And the most cases that you will ever get for evaluating your convolution will always be 6 cases. There will never be any more cases than 6 cases. You will only have to evaluate 6 cases being your maximum amount of cases for your convolution. So yes, it's tedious, but it isn't hard, it's just a lot of repetitive stuff. And yeah, I wouldn't give you anything more than 6 cases to evaluate. So yes, you combine the equations here for simplicity when you have the equation spanning for the same time ranges or different time ranges accordingly. So t plus 1 exists for -1 less than t less than 0, but also for 0 less than t less than equal to t less than 1. So we can say t plus 1 exists for -1 less than equal to t, and then we say less than 1 here, instead of writing the 2 lines over again as of such. So yes, you can combine these two lines here because it's the same output equation, just that it's going to be for these two time ranges here only. So you just combine the two time ranges here. And the reason why we write the piecewise continuous function is because we have different equations for different time ranges as a result of the convolution process. Alright, so are there any particular questions regarding this particular problem or anything regarding the convolution process that needs to be made more clear or that requires a little more explanation as of such? So we have a question next, and could the boundaries of h t minus tau have been t and t minus 2 like the first example? No, they cannot be the same for this case because we saw that the intercepts for this h of t were at positive 1 and negative 1 instead of it being 2 and 0. But if you compare the answers here for this example and the previous example, you're going to see that each one of these values here was shifted by 1. So the time ranges here were also shifted by 1, and the equations here were also shifted by 1 when you compare the results of this example and the previous example. So you would have seen for the previous example, this equation here would have been t for 0 less than equal to t less than 1, and then t here for 1 less than equal to t less than 2. And then for the resultant time ranges here, you'd have seen this being 4 minus t. And the resultant time ranges here would have been shifted accordingly as well. So this would have been 2 less than equal to t less than 3. And then 3 less than equal to t less than 4. And then you would have had 0 for t more than equal to 4. And this is just to show you guys an illustration that if you shift your x of t signal, if you shift your h of t signal, all the outputs here on the convolution also shift accordingly as well. And that shift is determined by how many units that h of t signal was shifted by. So you don't have to reperform an entire convolution if the h of t signal has been shifted by a certain amount of units and you have already performed the convolution for the same two signals, just that they're in different positions as of such. You just add the offsets accordingly to the output equations here of y of t, as well as for the time ranges as well. So yeah, just when you compare the answers for this example and the previous example, you'll basically see that all the output equations here have been shifted by 1 unit, and all the time ranges here have also been shifted by 1 unit accordingly. All right, so I don't think we have any further questions at this point in time regarding this. So let's go back to our lecture. Right, okay. So for homework, I want you guys to actually attempt this convolution here in particular. And what you're going to see here is that for x of t signal, we know that this rising here edge here is going to be t, and this falling edge here is going to be 2 minus t accordingly. But when we transform this to x of tau, and we use h of t minus tau here, when you start applying the convolutions as of such, you want to see that it gets a little bit tricky accordingly for when you start evaluating the convolution integral. And a good hint to say, or a good resource that you could use that's on the MyLearner website would be the link to the convolution examples that is on the top of the MyLearner page on the video resources. If you watch that, there's a full walkthrough for actually how you can evaluate the convolutions with different types of signals, being the square signal here and the triangular signals of such, and you basically get a full walkthrough if you're watching. I will also link that video resource in this video as well when it's finished recording and processing, for people who don't have access to MyLearner, so that way they can get access to it and see those particular examples as of such. So for homework, attempt this convolution, and I will post up the solutions for these if it's not on the video resources, and you can see how this convolution actually is evaluated and obtained accordingly as well. Alright, so that basically brings us to the end of our convolution lecture, and if there are any further questions regarding the topic of convolution, please ask them now. Otherwise, we'll be moving on to the final lecture for today, which will be first and second order systems. Alright, so it looks like we don't have any further questions regarding the topic of convolution, so I can end this lecture here. We go on to our next lecture, which is going to be first and second order system responses. So this particular lecture, we're going to just recap a little bit because we had to observe first and second order system responses earlier on in a previous lecture. We saw this in particular when we were solving for the differential equations to get the first and second order equations as of such, and how the responses were being when we actually plotted them in the time axis. So we just have to recap a little bit because we're talking about the first order and second order differential equation general forms. So basically, when we had a general form of a first order differential equation, and we conducted a Laplace transform for this equation here, we obtained our y-of-s equation here, meaning that we had the initial conditions represented by y0 negative, and then our steady state conditions here represented by our x of s component here as of such. And the y-of-s component here would be in our output signal. And then we also saw that if our initial condition here, y0 negative, was 0, where y of s is our output, this y of 0 negative being our initial condition response, and the x of s component here being our input response. When this goes to 0, we are just left with our input response here accordingly, giving us this equation. If we carry across x of s onto the left hand side here, getting y of s divided by x of s, this remains with this part here being our transfer function, which we represent as g of s. And we also remember that if we had y of t for an impulse response, that means that the impulse being delta of t mapped to x of t. When we do the Laplace transform for this, we get x of s being equal to 1. So as of such, we'll get y of s just be equal to our g of s transfer function. We can then perform partial fractions on this and divide it out as of such, and we can obtain our equivalent y of t equation here regardless. So after we do our partial fractions here, sorry, not partial fractions, after we divide out accordingly, and then we get our components for a and b and do, well, yes, it's basically partial fractions, sorry. So after we do our partial fractions here and we solve for a and b accordingly and we get our components, we can then use the inverse Laplace transform by the Laplace transform table to get our y of t signal here accordingly as of such. So if we plot this y of t signal, we see here that the b1 delta of t here represents our start point for the graph. And then our exponent form here represents the general shape of the graph throughout the entire equation for y of t. The important things to note regarding the impulse response for this y of t equation is that this system is never sinusoidal. So there are no oscillations in this system whatsoever. It's just a steady decay towards some steady state value as of such. So this will hold true for any first order differential equation that you are solving for. There will never be oscillations in a first order system. It will always be a steady decay or a steady rise to some steady state value. And once you hit that steady state value, it will remain constant throughout the entire time period. If we evaluate this for the step response, we basically know that the step response being u of t, when we watch this on the Laplace transform table, because it's going to be mapped to x of t, we'll get x of s equal to 1 on s. And we multiply this accordingly, and we separate this into partial fractions, and we solve for our components k1 and k2. We see here that the k1 component looks like our system transfer function that we just now saw. And because this is s plus a, and this a here represents a root of the system, this actually represents the transient response component of our system. And this form here for our transient response will not depend on the entire signal. But this k2 on s here, which is our second component, will determine our steady state response because there's no root on the denominator. And this form of the signal will be dependent upon it. So let's watch this accordingly for our typical resistant capacitor circuit, where we try to evaluate our step response. So once we put in x of s here being 1 on s, and we evaluate this accordingly and get our partial fractions, and we do our inverse Laplace transform to obtain y of t accordingly, but we know our component here without the roots on the denominator is going to be our steady state response. Our component with the root here is going to be our transient response. We basically see what our output equation is going to look like. So the output equation when we do the inverse transform is going to be y of t equal to u of t minus e of minus tau t here accordingly. But if we watch u of t, this is going to be this blue line here, where it represents a constant value of 1 for t more than or equal to 0. And our e of minus tau t here, which will represent this negative decay in exponent here, was similar to our results being our steady state response, as we can see here being 1 on s plus tau. Sorry, our transient response, sorry. being 1 divided by s plus tau. So the 1 and s component here being a steady state response will transform to u of t here accordingly, giving us this unit step here, for t more than equals to 0, being a value of 1. And then our transient response, which has the root on the denominator, gives us our negative decaying exponent graph here accordingly. When we combine the two here in a difference form, we see that the end result is going to be an increasing exponent graph here towards some steady state value as of such, or a system step response. And in general, for step response, even though it's the opposite of the impulse response where you saw it decayed accordingly, in this case for step response it increases to some set value. It also holds the same properties as the impulse response, where the step response cannot be sinusoidal and there are no oscillations present within the entire system. Alright, so that's basically the end of our first order impulse response and our first order step response analysis. Are there any particular questions regarding the first order systems at this point in time? Alright, so there don't seem to be any questions regarding the first order's impulse response and step response. So let's move on to our second order systems in particular. So we know that the general form of a second order differential equation was in this form here, where we had a d2y term and a dy term and a y term, and similarly we had a d2x term and dx term and an x term. And we assume all the initial conditions on the inputs was going to be 0. When we evaluate y of s, we get this form of equation here, where we had y of s being our output response, all our initial conditions being y of 0 negative here, and y prime of 0 negative being our first differential, will be our initial condition response, and our x of s component here was being our input response. If we assume that all the y 0 negative components here are also 0, and we'll be left here with y of s equal to this x component here, and once we carry across the x component being y divided by x, we'll obtain our transfer function here being g of s left by the multiplicative component that we saw in the previous slide. Now, for homework, I want you guys to actually attempt solving these two differential equations here to obtain a y of s equation and an x of s equation. And the answer is given to you here to verify that you actually did the steps accordingly. So, for homework, attempt getting this in the form of y of s equals to g of s, x of s. And basically, you will get the end result being this form here. So you actually have an answer to actually verify this, and you also have all the initial conditions here being 0 when you transform these equations here into the Laplace domain. So continuing on with our second order system evaluation, if we evaluate any general second order system here, impulse response, and we saw basically our impulse response here was going to be x of s equal to 1, In this particular case, for y of s being our answer here, if we partial fraction this accordingly, we see that the denominator here being s squared plus 6s plus 8 will resolve into s plus 2, s plus 4. And when we partial fraction it, we solve for the constants on top, we get both values being 1 here accordingly. When we do the inverse Laplace transform, we see we get a y of t signal here represented by a difference of two negative exponent signals. So the s plus 2 will transform to e to the minus 2t, and the s plus 4 will transform to e to the minus 4t, and these are separated by a negative sign here. And what you observe here in particular is that the e to the minus 2 signal is given by this decaying green line here. The y of t signal, as a result, would be our red line here. And this negative e of minus 4t will be an increasing signal here as of such. But when you combine the two, you see that we have a small oscillation here, which we refer to as an overshoot. And when we approach gradually towards some steady state value. So this is the result of an input response for a second order system. Basically, the combination of these exponents give us a small oscillation, which we refer to as an overshoot within the system, and then we approach gradually towards a steady state value as a result of this impulse response for a second order system. If we evaluate the step response for the second order system, let's consider the following abstract second order system here. Basically, we say b, a naught, and k are constants as of such. We evaluate the step response knowing that x of s is going to be 1 divided by s. When we evaluate the denominator here, in abstract math, we basically, when we do the quadratic equation, we get the roots here being a naught plus k plus root of k squared minus 1, and then a naught plus k minus the root of k squared minus 1 accordingly. And then we can partial fraction that accordingly as such, and we'll see we get the a component here being divided by s, the b component here being divided by the first root of the quadratic equation, and then the c component here being divided by the second root of the quadratic equation. But what we're going to observe here in particular is what's going to happen to this equation as we modify the values of k here to see what the step response looks like. So when we do the inverse Laplace transform, that a on s component becomes au of t, and these roots here accordingly will transform into negative exponents as of such. But we're watching this with respect to how the k value here is going to change and what's going to happen to our output graphs accordingly for the step response of a second order system. So for our first case, we're going to consider if k is less than 0. In this case, k is going to be a negative value. So the unit appears independent of k, so it's unaffected. But if k goes negative here, the result here will result in a negative value, and we have minus a naught, meaning that the entire exponent here will result in a positive exponent. So you have minus a naught multiplied by some negative value here, resulting in an entire positive value here for the power. Similarly, for this component here being the c component, we also get the same thing as well. And we know that for positive exponents, if we plot this, this basically shows us that our system is going to be unstable. So for any negative value of k, and typically we say less than 1, negative 1, less than k, less than 0, for this range of k values, for the second order step response, you will get an exponentially increasing sinusoid for y of c. And as such, that means your output is also going to be exponentially increasing. So when k is less than 0 for this case, that means the y of s system, being our y of t, represented in the time domain, will result in an unstable system. Now let's watch what happens if k is more than 1 in this particular case. So the unit step is also independent here as of such. But these exponents here, when k is more than 1, this bracket component here will result in a positive value, but we multiply by negative a naught, so we get a negative value overall for the power of the exponent. So the exponent here is going to be negative, for the B component, and similarly for the C component, it's also going to be negative as of such. A negative exponent results in stability. So typically we say for the range of k lying in between 1 and 2, we get an exponentially decrease in sinusoid resulting in an exponentially decrease in output. So for values of k more than 1 for a second order system, and we evaluate the step response, that means the y of s system, and conversely the y of t system, results in a stable system entirely. So what happens if we go in between the two ranges? And we say in this case we go for k being between 0 and 1. The unit step here is also independent of k, as we saw for the last two slides. But because k here is a positive value, but it's in between 0 and 1, the exponent here is negative, but it isn't truly stable. Similarly, for the C component here, it's also negative, but it's not really stable. So we're going to have to observe this visually to understand why we don't say it's fully stable accordingly. So let's watch this accordingly for a general second order system equation, and if we substitute values here accordingly for k, we hold a0 and b constant accordingly. So we're going to observe this for when k is going to be a negative value, k is going to be a positive value greater than 1, and then when k lies in between 0 and 1, and we're going to observe the effect of y of s, and when we transfer it back into y of t, and we plot the output graphs accordingly. So if we do the step response here for y of s after we substitute these values for a0, k, and b, we basically see for k being a negative value, we have an exponentially increasing sinusoid, resulting in a totally unstable system. Because this value here never approaches its steady state value. It just keeps on going towards infinity out of such. For our next example here, a0 and b basically are the same values, but k here is going to be a value greater than 1. So when we substitute these accordingly into our y of s equation, and we get our result on y of s equation, and we do the step response to this, we basically see that we get a negative exponent here, which basically gives us a stable system, because our system here, k being more than 1, results in a rising graph here that approaches some steady state value after a certain set point in time. So for k more than 1, we end up with an entirely stable system. Our last example here for a second order system will be when k is going to be in between a value of 0 and 1. And we plug in our values here accordingly as well for y of s. We get a different y of s equation because k here is different, and we're going to evaluate the step response here. We see that for when k lies in between 0 and 1 in particular, we see that we get this nice rising graph here, but then we have a small oscillation as of such. So we have some oscillation that occurs before we actually approach a steady state value accordingly for step response here. And this effect is observed for when k lies in between the values of 0 and 1. So yes, it is stable because we eventually approach a steady state value, but initially we have some oscillation before we actually approach the steady state value. And this is true for when k lies in between the values of 0 and 1. So the initial oscillation here, which is given by the maximum peak that you observe, minus the steady state value that you achieve at the end of the graph. The difference between the two here is what we refer to as an overshoot value. So this overshoot value is given by the difference between the maximum peak and the steady state value that you achieve at the end of the graph. If we decrease the value of k in between 0 and 1, so we just now observe this here for k equals 0.5. If we say k is equal to 0.2, you see that we get more oscillations as of such. And then we typically approach a steady state value, but it takes longer time before you actually approach that steady state value. but a different value of k here being closer towards 0. And once you get this kind of oscillation here that keeps on repeating itself but negatively decays to some steady state value, we refer to this effect as ringing. If k was 0, the entire system would just oscillate as such and will never approach a steady state value. So we'll just get a fully unstable system. So in watching the terminology for a second order system, we watch this with respect to how we can actually map this to physical components. So omega naught here being our constant component on the denominator as well as being a constant component that could also exist on the numerator is what we refer to as the system natural frequency or resonant frequency. And the units for this is measured in radians per second. The k value that we have been observing, or in some textbooks we refer to this as zeta, is also referred to as our system damping factor. And this damping factor determines how fast we achieve stability within the system, if it is actually achieved. And it determines if the system is stable or not, depending on the value it takes. Which we saw in the last few slides, where if it was a negative value, it would be totally unstable. If it was more than 1, we will get a stable system. And if it lies between 0 and 1, we'll get a little bit of oscillation before we hit the steady state value, resulting in an overall stable system as such. And in most textbooks, you will see the second order system equation being represented by this form here. So remember, omega naught here is the system natural or resonant frequency, and k or zeta here on the denominator, represented by the s component, is what we refer to as our system damping factor. So when zeta is equal to 1, and remember zeta is just basically k, the system here is not going to be underdamped, and the system here is not going to be overdamped. The system here is just going to be critical damped as of such, because it's actually at 1. As of such, you get this nice rising value here towards a steady state value. Sorry, a nice rising graph here towards a steady state value, but no oscillation required. Alright, so yep, that brings us to the end of our first and second order systems lecture. Are there any particular questions regarding the material of this lecture at this point in time? Alright, so there doesn't seem to be any questions in the chat at this point in time. So if there are any questions regarding the material of these lectures, you can leave a question down in the comments below, or you can feel free to email me and I will reply to you accordingly to regards to any queries that you have as such. So for next week, in particular, at this point in time, we've covered enough material for me to actually post up problem set 2. So I will post it up either by today or tomorrow if as such. I know I also promised you guys yesterday that I need to post up solutions for one of the lectures in particular. This would have been the solution for the Laplace transform. So I will post up those solutions as well either later today or tomorrow. And I will like for you guys to attempt problem set 2, and like problem set 1, I will post up a poll for you guys to vote on the top 3 questions that gave you the most problems for us to actually attempt next week Tuesday during the tutorial session. Next week in particular, we will only be doing 2 lectures, and the reason for this being is that the material for those 2 lectures are going to be based on block diagrams, because the first lecture is going to be on block diagram representation, and the second lecture is going to be on block diagram simplification. And this forms a very important part in your final exams in particular, because these questions tend to come for like 10 marks off of your 100 marks in the final exam. So, just recapping, next week's lectures are going to be entirely on block diagram representations and simplifications, and I will be posting up problem set 2 for you guys to attempt, as well as the poll for you guys to vote on which 3 questions gave you the most problems for me to do live on next week's Tuesday session during the tutorial. And I will also post up the solution that I promised you guys yesterday for the Laplace transform in that particular lecture that we covered. So, until then, take care, be safe, and I'll see you guys soon. Later.